All right, let's talk about the invisible giants all around us. I'm talking about polymers. You can't see them as individual molecules, but they make up pretty much everything in our modern world. They are everywhere. So today, we're going to peel back the curtain and look at the surprisingly simple chemistry behind these amazing materials. So let's start with a bit of a riddle. What do a plastic bottle, a nylon jacket, and your own body have in common? I mean, they seem totally unrelated, right? A piece of clothing, a disposable bottle, and, well, you. But there is a common thread, and it's a special kind of molecule that connects them all. The answer? Polymers.
So what exactly is a polymer? Honestly, the idea is super simple. Imagine you have a ton of paper clips. Each one of those clips is a monomer. Now, when you start linking them together, one after another, into a really long chain, you've just made a polymer. It's just a giant molecule built from small repeating parts. And get this, the proteins that make up your muscles, they're just natural polymers made from amino acid monomers.
Okay, so how do we actually build these massive chains in a lab? Well, there are two main recipes we're going to look at. The first one is the simplest, and it's called addition polymerization. The name kind of gives it away, right? You just add the monomers together. But you do need one very special ingredient to get the whole reaction started. And that magic ingredient is this, a carbon-carbon double bond. You can think of this C=C bond as a pair of hands holding onto each other really, really tightly. To build a chain, you just need a way to break one of those handholds, freeing up a hand to grab onto the next monomer in line. And this is exactly how it works. You start with a bunch of individual monomers, like ethene, and they each have that C double bond. Then you kick off the reaction and bam, that double bond breaks open. This creates a connection point on each side of the molecule. And then they just start linking up end to end, creating one super long chain we call polyethylene. And notice, in the final product, all those double bonds are gone. It's just single bonds holding the whole thing together. All right, on to our second recipe. This one is called condensation polymerization. It's also about linking monomers into a chain, but this time, the process is a little messier. There's always a little something left over at the end. And this is the absolute key difference between the two methods. With addition polymerization, you put the monomers in, you get the polymer out. Clean and simple. But with condensation polymerization, when the monomers join up, they spit out a small molecule, almost always water. So it's not just A plus B equals AB. It's A plus B equals AB plus a tiny water molecule. A fantastic example of this is nylon. You've definitely heard of it. Now, it's built from two different kinds of monomers that have to alternate. Don't worry about the long chemical names there. Just think of it like linking red paper clips to blue paper clips over and over again in a perfect pattern. So as these two different monomers link up, they form a special bond called an amide link. And here's the key part. Every single time a link is formed, poof, a water molecule is lost. It's condensed out. This happens millions of times, and that's how you get the incredibly strong and durable polymer we know as nylon. Now, for an example you're probably holding right now, or at least have in your fridge, PET. That's the clear plastic used for soda and water bottles. Just like nylon, PET is a condensation polymer made from two different kinds of building blocks. And the process is, you guessed it, very similar. The monomers connect, forming a different kind of bond this time called an ester link. But just like with nylon, every time a link is made, a water molecule gets kicked out. This is the chemistry that creates that strong, clear plastic that holds your drink. So we've seen how amazing these polymers are. They're strong, they're durable, they're incredibly useful. But here's the catch. The very thing that makes them so great is also the source of a huge environmental problem. They are, in a sense, too good at their job. They're built to last and last and last. And this right here really gets to the core of the problem. Most plastics are non-biodegradable. What does that really mean? It means that the little microorganisms in nature, the things that break down leaves and food scraps, they just can't digest plastic. Once we make it, it's pretty much with us for hundreds, if not thousands of years. So when we throw that plastic bottle away, where does it actually go? Well, there are three main and, frankly, pretty bad options. They can end up in landfills, where they just sit there, taking up space forever. We can burn them, but that can release greenhouse gases and other toxic stuff into the air. Or, and this is the really tragic one, they end up in our oceans and rivers, where they cause unbelievable damage to wildlife. But what if we could hit the rewind button? What if we could reverse the whole process and unlink those long polymer chains, turning them back into the simple monomers they started as? Well, this is where the science gets really, really cool. It's all about trying to close the polymer loop. And the scientific word for this is depolymerization. It's literally the exact opposite of what we talked about before. Instead of building long chains, we're trying to carefully break them back down, piece by piece, so we can get those original monomer building blocks back.
So can we do this for all plastics? Well, not easily. It turns out some plastics are much better candidates than others. And guess who the star pupil is? Our old friend PET, the plastic bottle polymer. It's actually pretty easy to depolymerize.
And scientists have found two really clever ways to do it. There's a biological way, using enzymes from special microbes that can literally eat the plastic and break it down, and there's a chemical way, using solvents and heat to achieve the same thing. Now, you might be wondering, why does this work so well for PET? Well, remember how it was made? By kicking out water to form those ester links? It turns out those links act like a built-in break-here point, a sort of chemical weak spot that enzymes and other chemicals can easily attack and break apart. It's much harder to do with addition polymers that just have that super strong carbon backbone. The ultimate goal here is to create a perfect circle. We take old PET plastic, break it down into its raw materials, the monomers, and then use those exact same monomers to make brand new, high-quality PET plastic. We wouldn't have to drill for more oil to make new plastic. It's true chemical recycling. So we're left with this really powerful idea. The same clever chemistry that let us build all these amazing materials might just give us the tools to unbuild them sustainably. But that leads to one final, really big question. We have the science, we have the chemical tools, but is clever chemistry really enough to solve a problem that's so deeply tied to how much we buy, use, and throw away every single day? Something to think about.